In this video, we are going to discuss about buck boost converter. Buck boost converter is a type of DC to DC converter. It has an output voltage magnitude that is either greater than or less than the input voltage magnitude. For example, we used to get the output right. Thus, V naught by Vs is equal to d divided by 1 minus d. So if d is nothing but your duty cycle, so the d value ranges from 0 to 1. So if d value is 0.5, okay, so d values it ranges from 0 to 0.5. Then this will act as a, you can see, let us substitute the value and see. If I substitute d is equal to 0.1, then V naught by Vs is equal to 0.1 minus 0.9. So this is nothing but 1 divided by 9. So V naught is equal to 1 divided by 9 times Vs. So V naught is less than Vs. So this is nothing but your buck converter. Okay. Suppose if d ranges from 0.5 to 1. For example, let me take d is equal to 0.6. So 0.6 divided by 0.4, that is nothing but 3 divided by 2, that is 1.5. So V naught is equal to 1.5 times of Vs. So V naught is greater than Vs. So it is a boost converter. Okay. So it can either act as a boost or buck converter based on the value of d. D is nothing but a duty cycle. So this is equivalent to a flyback converter, which is using a single inductor instead of a transformer. So let us discuss the diagram for buck boost converter. So you have a switch. It is either a MOSFET or a switch. Okay. So this is your input supply, followed by a inductor, followed by a Schottky diode, followed by a capacitor, and this is your output. Okay. So here I am taking the output as an inverted output. Okay. So what happens when the switch is on? Okay. During switch is on. So when the switch is on, the inductance get charged, right? So what is the value across inductance? Inductance is equal to Vs, because whatever the current from this Vs input source will charge this, will make the inductance to charge. So the voltage across the inductance is Vs. Okay. So let me assume this is your this is the time where the switch is on, and this is the time where the switch is off. So the current across the inductance will increase when the switch is on. Okay, this is IL. So here when the switch is on, when the switch is closed, you will get the IL current. Therefore the voltage across the VL is nothing but Vs. So I can draw the voltage across the inductance. VL is nothing but Vs. Okay, when the switch is closed. So when it is open, what happens? It will not flow in this direction, right? So since the switch is open, VL is not connected to Vs. Therefore, it will charge the capacitance in this direction. Okay. So since it is charging in this direction, I can draw this one as plus minus. Okay, so I'm getting a inverted output. Therefore what is the voltage across the VC is, and the diode is short circuit, right? So what is the voltage across the VC is nothing but minus of VL. Okay, so I can write VL is equal to minus VC. So what is the voltage across the VL? VL is nothing but minus VC when the switch is closed. Okay, so this is nothing but minus VC. So this is the current that is IC, this is the current that is I naught, which is flowing in this direction, and this is nothing but ID. Okay, so what is ID? Using Kirchhoff's current law, ID is equal to IC plus I naught. So if I want to find the value of ID, so what is the value of ID? ID so ID is 0 when the switch is closed, right? So there is no current will flow through the ID when the current is when the switch is open. Okay, so this is 0 till the switch is closed, and when the switch is open only, what happened? There is a current flow in the ID that is same as that of IL. Okay, so whatever the current which is in IL, which will flow through the ID, so this is same as that of IL. Okay, and when the switch is closed, it goes to 0. So this is the value of ID. So now I can draw for IC. Okay, so what is IC now? So this is your IC. I can write IC is equal to ID minus I naught. So ID is 0 for T on. So what is value of IC? IC now, IC is equal to minus I naught. Okay, IC is equal to minus I naught, and when the switch is off, this is nothing but ID minus I naught. So this is the output. Okay, So let me copy this one and draw it in the next page. So what is the actual output I will get? So this is your V naught. Okay. This is your V naught, and during this time, okay, during this time, what happens? Capacitor is discharging. So when the capacitor is discharging, you will get a very less output, and when the capacitor is charging, you will get the higher output. Okay. So this is how is a actual output. Okay. So this is your actual output of V naught. Okay, and this is nothing but del L, del I. Okay, so now I can write T on plus T off is equal to 0.5. Okay, so what is T on time? T on time is this is your T on time. Okay, this is your T on time. So this is nothing but so T on time Vs into T on. So T on into Vs minus Vc into T off is equal to 0. So from this diagram, okay. So I can write Vs by Vc is equal to T off by T on. So this T off I can write as 1 minus T off. Sorry, 1 minus T on, because we know that T on plus T off is equal to T. Okay. So I can write Vc by Vs is equal to T on divided by T minus T on. So divide the both the equation by T. Okay. So T on by T and T by T minus T on by T. So this is equal to D divided by 1 minus T. So we know that the Vc is nothing but V naught. Okay. Where D is equal to T on divided by T. This is your equation for duty cycle. So in a similar way, I can write in order to find the value of inductance. In order to find the value of inductance, I can write VL is equal to L di by dt. L dl by dt. So what is the value of VL when T is T on? VL is equal to Vs del L del I divided by T on. So when T on, the VL value is Vs. Okay. So what is the value of when the it is off, when it is t off, during the t of time, it is minus Vc, and this del I is decreasing, so I can write this is minus del I. Okay, so I can write Vc is equal to L di divided by t off. Okay, so from this equation I can write T on is equal to L del I divided by Vs. So from this equation I can write T off is equal to L di divided by Vc. So T on plus T off is equal to L di, I can take it a common, so 1 by Vs plus 1 divided by Vc. So this is nothing but L del I into Vc Vs divided by Vs plus Vc plus Vs divided by Vc Vs. So this is nothing but your T, right, from this equation. So I can write L is equal to T Vc Vs divided by del I into Vc plus Vs. So here the Vc is nothing but V naught del I V naught plus Vs. Okay, so this is the value of the inductance. Next, in order to find the value of the capacitance, so we know that Q is equal to del Q is equal to C into del V, and we know that I is equal to dq by dt, and I can write Q is equal to integration of IC into dt. So if I want to integrate this one, the integration value is nothing but the area of this one. So what is the area of this one? Area of this one is I naught. So this value is nothing but I naught into T on. That is your value. So I can write C del V is equal to I naught into T on. So from this I can write the value of C is equal to I naught T on divided by del V. So this is how you have to find the value of C. So next let us discuss about application of this buck boost converter. So first application, it is used in the consumer electronics. Next it is used as power amplifier, and it is used in adaptive control logic. Next it is used in battery power systems. Next let us discuss about the advantages of buck boost converter. So the first advantage is it gives high and low output voltage using a minimum component, right? So with the very less component I can able to achieve the higher and lower output voltage. And next one is it operates with lower duty cycle. Okay, next it is very less expensive. So next let us discuss about the disadvantage. So here the switch we have used that doesn't have a terminal at ground. And next one is since the output is inverted, which results in complex sensing and feedback circuits. So next one is the high gain cannot be achieved with this connection type as the efficiency is poor, and the input and the output so the input current and the charging current of the output capacitors here is discontinuous. So I hope this video is useful for you. Thank you very much.